polymer chemistry topics to wrap up our polymer section. I want to talk about two different Nobel Prizes in this video. The first is back in 1963 when Ziegler, German, and Nada, an Italian, won the Nobel Prize for figuring out a better way to do a polymerization. Again, we talked about some of the problems with especially radical polymerization. It gives you chain branching because your branches can sort of stop and start, transfer a radical, and start to branch off in the middle of a chain. We want to try to avoid that to get longer chains and stronger materials. And the way they did that is to design an organometallic catalyst, the fine details of which are both complicated and in some cases proprietary. But they're going to give you unbranched stereoregular polymers. And again, the unbranched is important because if I just say take ethylene here and try to polymerize it by radical conditions, it's going to require a little bit of heat and a little bit of a radical initiator, but I'm definitely going to get lots and lots of chain branching in that compound. So I get a highly branched, low density PE. So we call this LDPE, low density polyethylene. But if I use this polymerization method, I'm going to get long, straight, unbranched chains that are going to kind of be like the stack of logs that we talked about earlier on. So a more crystalline polymer, higher density. So when you see HDPE, that's high density polyethylene. So when you think about like a Tylenol bottle, if you look in the bottom of a Tylenol bottle, you'll see the little 2 with the recycling arrows over it, and you'll see HDPE. That's high density polyethylene. Low density polyethylene really is only good for like fill or really, really cheap film covering and something like that. So there's a big difference, even though both of these are just CH2s and that's it, there's a big difference in the mechanical properties of these things due to their morphology. If we look at stereoregularity, that means that if we're creating a stereocenter every time we add a monomer, are those stereocenters all the same or different or random or what? That's called stereoregularity or tacticity. If something is atactic, then say this is polypropylene, right? So if I just had another methyl on ethylene and had propylene, I would get polypropylene. This is often used in long underwear, for instance. Atactic polypropylene is random, so the stereocenters are randomly distributed. Isotactic polypropylene would have all the stereocenters the same. Or syndiotactic would have the stereocenters alternating regularly. These bottom two are going to stack a lot better, right? Picture stacking chairs on top of each other, right? If all the legs are going the same way, the chairs will stack well. But if the chair legs are going in random directions, they're just not going to stack as well. And remember, better stacking means better intermolecular forces, right? Closer packing. And better intermolecular forces means a higher melting point. Okay, so for instance, we talked about not being able to boil polyethylene terephthalate bottles. Right, we can't reuse those bottles just by autoclaving them, for instance. The same is true with atactic polypropylene. I can't. The TG is under 100 degrees, and so I can't just boil it in water to sterilize it. But if I have isotactic polypropylene, then I can get TGs over 100, and I can reuse those bottles by autoclaving. So this is a non-trivial difference. And again, with different Ziegler-Nada catalysts, I can access both of these stereoregular polymers, the isotactic and the syndiotactic. I can give you the rough cartoon sketch of what this mechanism looks like. So this is kind of complicated organometallic catalysis. So here I've got this titanium thing. I'll just show that these rings are actually very stable aromatic anions called CP rings or cyclopentadienyl. So they're just basically ligands that give that metal a few electrons. You'll learn a lot about that if you take inorganic chemistry from Professor Sazima. So here I've got some catalyst that is essentially being methylated here, so I get this intermediate. And so the magic of all of this setup is that the titanium atom controls how the monomer is attaching and grow to the growing system. So here the titanium grabs this alkene. The alkene binds to it more or less end on, pi bond to metal. And then this rearranges to insert this carbon onto that carbon to make a new carbon-carbon bond here. Now that creates a new open site on the titanium that can grab a new monomer. That adds into the growing chain. I have a new open site over here, and it keeps going on and on. So again, I know this is way, way past our level that we're trying to cover in Chemistry 252. But the main point here is that where the alkene adds, more or less like goes back and forth on the metal atom. So on the top and the bottom, on the top and the bottom. So it's almost like I'm trying to build a chain, and I keep handing off the growing chain to one hand while my other hand grabs the monomer. Okay, insert here. Now that hand grabs it. And now insert there. That hand grabs it. Insert here. That hand grabs it. All right. And so by that idea, I'm able to A, always have growth at the end and nowhere else, and B, I can even, if steric effects are going to keep R kind of away from my titanium, I can even control stereochemistry like this, right? Especially if I get more complicated stuff over here that creates a chiral environment. So this is pretty cool. Again, just like when we talked about Suzuki and Sonogashira, these organometallic catalysts give me a lot of control over the system. And I can use that control to get stereo-regular polymers that are very long. Very important. Our next Nobel is in 2005 when Grubb, Schrock, and Chauvin won for alkene metathesis. So skipping to the end, what happens in alkene metathesis is that we start with two alkenes and we end up with two alkenes, but the alkenes more or less switch partners here. So what these two carbons on the end more or less bond, and you end up with, instead of two horizontal double bonds, two vertical double bonds between the same carbons. And so this is an equilibrium process. It's catalyzed by some pretty fancy metal catalysts. And what makes this fancy is that there's actually a metal carbon double bond. It's actually a pi bond there, which again, if you take 320, you'll talk a lot about. But here, this is under equilibrium control, and you can see how we might affect the equilibrium, right? If I want to push it to the right, all I need to do is get rid of this ethylene that's formed, which is easy because this is a gas, right? All I need to do is more or less run this and keep blowing nitrogen through it and evacuating all this that's formed, and eventually I'll get all ring-closed material. In the same way, if I wanted to go to the left, I'll just pressurize the system with extra ethylene. Okay? And if you're wondering, can two molecules of these come together to form a longer chain? Yes, they can. That's why if I wanted to do this, I would run it very dilute. But that very chain-making system with molecules reacting with each other is how our polymerization is going to work. Let's talk about the use of alkene metathesis in polymerization. So this is ring opening metathesis polymerization, or ROMP. How does ROMP work? So we're going to start with a monomer with a double bond there, an alkene monomer, and that alkene should be a little bit strained. That's going to help push our equilibrium to the right. So here the strained alkene is going to react with our catalyst, and so the catalyst more or less makes a four-membered ring. So we can kind of think of the electrons adding in like this. That four-membered ring will break down the different way to, instead of breaking these bonds and going backwards, breaking these bonds and going forwards. Now this is simply this drawn differently, and now this ruthenium site, this metal site, got passed to this carbon. So now there's a new ruthenium carbon bond that can add into another monomer and get something like this. So again, I don't expect you to know the mechanism for this stuff. It's a little bit out of our league. But I wanted to show you that we're able to make this all carbon plastic, right? This is going to be a pretty strong plastic because it's stereo regular. There's no opportunity to mess with the stereochemistry here. and it's going to be very, very linear. We're going to have very long chains because this is very well controlled. And so here's the pitch. Let's say you are trying to design a space shuttle hull, and you want a plastic that's going to heal itself, right? So as a space shuttle is flying through space, if you get like a little cracks that develop in the plastic coating, then you don't want to have to spacewalk outside to go like spackle a hole in the spaceship, right? In the space shuttle. We want to have a self-healing polymer if possible. And so what you can do is design a polymer like this, but in that polymer put microbeads, little plastic microbeads that contain unreacted monomer, and then other beads that contain a little bit of the catalyst. So you've got this plastic with these beads sort of embedded in it. When the plastic develops a crack, these beads crack open, and a little bit of the monomer comes out and a little bit of the catalyst comes out. And so you actually get a polymerization in situ. So in the crack, you start to release monomer that can start to knit up extra polymer where you need it. Self-healing space shuttle. Pretty cool. Again, it's made possible by cool organometallic catalysis. Very gentle, gives us excellent yields of a very linear, stereo, regular polymer. So very cool. Alkene metathesis, again, is widely used just in normal synthesis to open and close rings like that. But in this case, we can use it for polymerization.